just she broke up with me.
Now like we're ready, let's get to work.
What?
I'm a survivor, I'm not gonna give up, I'm not gonna stop, I'm gonna work harder, I'm a survivor, I'm gonna make it, I will survive, we won't survive.
Hi, we are the algorithm team. Our job is to control how the robot moves and make sure it gets around the arena efficiently.
We assign 4 directions, forward, backward, left, and right, to the robot. For path planning, we also implemented the A* algorithm to determine the shortest path to its target.
We apply a higher penalty for turns to encourage the robot to move in straight lines whenever possible to reduce unnecessary turns.
Also, if an obstacle is unreachable due to turning constraints, our algorithm skips it and moves on to the next one.
Of course, in real-world conditions, the robot may not precisely follow the exact path that the algorithm gives.
To address this, we ensured that the robot maintains a sufficient clearance, which is about 20 cm from the obstacle, to increase the chances of capturing images.
What better way for us to visualize our algorithm than displaying it in an app? This app is essentially the remote control of our robot. It connects to the Raspberry Pi via Bluetooth, allowing us to send and receive messages in real time.
Exactly. Once connected, the app will let us communicate with the robot. It's like texting your own robot. Pretty surreal, right?
But that's not all. We also have a grid map where the real fun begins. Here, we can manually and virtually control the robot. How cool is that?
We can even place the obstacles on the map by simply dragging and dropping them. Once all obstacles are in place, we send the information to Raspberry Pi for the algorithm to process.
Right. We just wait for the status confirming that the robot is ready to run. Then we click the Start Task button.
Wow, would you look at that? The robot is navigating and detecting the obstacles at the same time.
Next, image recognition to recognize and predict symbols accurately. For this component, we use the Raspberry Pi camera, the YOLO V11 model, as well as the inference server coded with Plus API and Python script. The overall pipeline are as follows. Firstly, collect all past semester data available online and perform training using YOLO V11 model. Secondly, to collect data using the Raspberry Pi camera for edge cases. Thirdly, utilizing the pre-trained model done in step 1 to annotate this data collected. Fourthly, further train the model with more data. And lastly, to create a heuristic to further improve the model for specific tasks.
The Raspberry Pi serves as a central controller in our system, handling the core decision-making and communication logic. In order for it to communicate effectively with 3 systems, we use a multi-threading approach. For communication between the RPi and Android, 2 threads are created, 1 thread for sending messages and 1 thread for receiving messages. This allows information to be sent and received at the same time without compromising on responsiveness. A similar implementation is used for communication with the STM32. Additionally, we use semaphores to ensure that only one sensitive action, such as executing a movement command or capturing an image, can occur at a time, preventing race conditions between concurrent threads. For communication between algorithm and image recognition servers, HTTP requests are used. Pi camera library is also used to take the picture before sending it to the image recognition server, with additional parameters used to make the picture grayscale and fit the resolution requirements of our trained model.
Besides using the RPi camera, other sensors used to aid in the robot navigation are the gyroscope, encoders, ultrasonic sensor, and IR sensors. For task 1, we use the gyroscope, encoder, servo, and motors. We implemented a state machine in the STM to streamline the processing of commands, such as which condition the STM has to check for before declaring that the command has completed. Then we perform a cleanup step. We implemented a queue-based command system to allow us to easily handle multi-step commands, such as turns, converting a single command, such as forward right, into 3 separate commands, forward, reverse, forward. Tightening of turning radius with the logic handled directly within the STM.
For task 2, the movements were generally built upon those in task 1. The challenge we faced for task 2 was the variable length of object 2. To overcome that, we utilized the IR sensor and encoder values to measure the length of objects 2 longer cycle. With the measured length and a 45-degree angle, we applied trigonometry to have the robot move along the hypotenuse. This ensured that the robot's IR sensor would be within range to detect object 1 when returning back to the car park.
And I'm happy to have met you.